Hello guys, welcome to my channel. Today we will be talking about a new model that came recently. It's called LongNet, and it's a model based on the transformer that came from Microsoft Research Asia just 2 weeks ago, I guess. And the basic idea is that they want to scale the transformer, but the wonderful idea is that they managed to scale it to 1 billion tokens. Now, if you're familiar with language models, you know that the sequence length makes a huge impact on the performance of the model, because the sequence length tells you how many tokens can relate to each other when performing the attention mechanism, which allows the model, for example, to have a longer context or a shorter context. For example, for a model like GPT, you want to be able to have a long context so that the model can watch words that were written a long time ago to calculate the next token, for example. And the LongNet is able to scale this to 1 billion token. So to show you how amazing this is, I want to show you this graph in which we show that, for example, the sequence length of GPT was just 512. And then we have this part transformer, 12,000, 64,000, 262,000, 1 million. But however, they go 1,000 times more with LongNet, 1 billion tokens. And just to imagine the scale, it's really amazing, because you can basically feed all the Wikipedia of the text of Wikipedia to the model, and the model will be able to calculate the attention using all these tokens. But let's see how this all works. First of all, LongNet, as claimed by the authors, has significant advantages. The first is that it is linear. The computational complexity is linear with the sequence length, and we will see why and how. There is a logarithmic dependency between tokens, so it means that basically the more distance the tokens, the dependency is less powerful, is less they are, how to say, the attention mechanism is less powerful between two tokens that are very far from each other, and more strong between two tokens that are close to each other. And it can be trained on a distributed network. It means that we can calculate this attention mechanism on a distributed system, so multiple GPUs or multiple computers. And it is a drop-in replacement for standard attention, which means that if we already have a model that uses the attention mechanism, we can basically just replace the attention mechanism without changing all the rest of the model, and it will work as before, but with this new improved attention that can use longer sequence lengths. And if you're not familiar with the transformer models, I kindly ask you to watch my previous video in which I explained the attention model, the attention mechanism, and the transformer model. And I will review it basically here to show you what was the problem with the attention mechanism before. So here I have the slides from my previous video, and we can see here the self-attention mechanism. With the self-attention we had before, we had a matrix called the Q, K, and V. And the Q was basically the sentence, which is a matrix of sequence length by D model. D model is the size of the vector of that representing the embedding of each word. And when we do the multiplication of query multiplied by the K, the transpose of the K, to produce this matrix requires a number of operations that is n to the power of 2 multiplied by the D model. Why? Because so it's n to the power of 2 multiplied by the D model. Why is this the case? Well, to produce, for example, this item here in this the output of this softmax, we need to do the dot product of this word, so the word your with the word your, so the word with itself, and the vector, the dot product of two vectors that are D model long is D model. And we need to do this for all the items in this matrix, and the items in this matrix are n to the power of 2, so the sequence to the power of 2. And this is the reason why the complexity of the self-attention before, but also of the attention, of the cross-attention before, was in the order of n to the power of 2 by D. And this table is also, this comparison is also present in the paper here. So the vanilla attention had a complexity of n to the power of 2 multiplied by D, but with this new model, the LongNet, we have an attention model, an attention mechanism that is in the order of n multiplied by, so it grows linearly with the sequence length. And we will see how. So here the introduction, the authors claim that actually the sequence length is one of the main problems with the language models, and how scaling it is a priority. And here they showed how this work is better than the other, basically because we reduce the number of computations to calculate the attention, and how they scale it to 1 billion. We will see all of this in detail. I will also show some visualizations of how this works. The basic principle is attention allocation decreases exponentially as the distance between the tokens grow. Now let's look at the picture to see how this works. Before we had, let's go to my previous slide. Before we had a matrix like this. So we calculated the attention between all tokens with all other tokens. But with the LongNet, we don't do this. Imagine we have a sequence length of 16. And of course, in the upper part of this matrix, we don't calculate the attention because we want the model, the attention mechanism, to be causal. So we don't want the token number 1 to be related to the token number 8. But of course, we want the token number 8 to be able to watch the token number 1, for example. And so all this part is empty. And the second thing is, instead of calculating all the attention, all the dot products of all the tokens with all other tokens, what we do is we split the sequence into small windows of different sizes. So first we start with a size of 4. In this case, the n is the number of tokens of this sentence. We split into 4 segments, here are called segments, each one of size 4. And we calculate the attention between all the words in this small box with all the other words. And we do it for all these small segments here. Here we also see another parameter called dilated rate, because we are not skipping any token. So we are calculating all token with all other token. We do it again, this time, however, by increasing the size of the window. So we don't use a window of size 4, we use a window of size 8. And we calculate the attention between each word and every other word in this window. So basically, and we do it all for all the windows until they cover all the sequence length. Again, then we double the segment length, so the size of the window that we watch, but we also double the deletion rate, so how many tokens we skip. So we relate the token number 0 with the token number 4, and then we skip 3, and then we do again the dot product, and then we skip 3, and we do again the dot product. So we skip every 3, here we skip every 1, here we skip 0. Why do we do this? Because we want smaller window, we want the attention mechanism to be more precise. Because if you, for example, when you read a book, you know, when you read a paragraph, the words in the paragraph should be very related to each other because they're talking about something very specific. This one can be thought of as a chapter. So in the chapter, we don't want to relate all the words of all the chapter to each other, but maybe some parts of the chapter to each other, because basically in the same chapter, the paragraph more or less will talk about the same topics, but it's not like we need the dot product between all the words in the chapter with all the other words in the same chapter. And then if we go to the book level, we don't want the dot product between every word of the book with all the other words, but we want some general idea. So basically we want some words so the general theme of the book should be present, but not every word with other words. So this is the idea that we use also for this attention mechanism here. For small windows, so words that are very close to each other, we do the dot product. So words that are more far from each other, we don't do all the dot products. And for very big windows, we do even less. Another thing is that the number of dot products in each window, no matter the size of the window or the deletion rate, is always the same. So here, for example, we have 4 plus 3 plus 2 plus 1 dot products in this window. And it's the same number of dot products that we have here, and it's the same number of dot products that we have here. Now, you may be wondering, well, this is not relating the token number 1 to the token number 16, for example, right? Yeah. But what if we overlapped all of them together? We obtain something like this. And you can see here that still the token number 1 is not related to the token number 16, but we can always find a connection, a way of going from token number 1 to token number 16 by using intermediate tokens. And we will see later how this is possible. I also made a tool to visualize this. And let's watch some details from the paper. So first we start by introducing the vanilla transformer. So this is basically the attention mechanism, as in the paper attention is all you need, and it's the same one that we saw here. Then basically here they describe what is the dilated attention. So in the dilated attention we choose a W and the R, so a window size and the dilation rate, and we divide our sequence into n divided by w boxes like this. Here n is 16. If the segment length is 4, we will have 4 boxes. If the segment length is 8, we will have 2 boxes, etc. And we also skip every r tokens, actually r minus 1 tokens. And all of these, actually, as you can see, they are independent, because here the attention mechanism to be calculated in this box, for example, you only need to have available the embedding of the tokens that are in this box, because there is no interconnection between these two boxes. So this one and this one can be calculated in parallel. Okay, and the next thing is that they calculate the softmax for each boxes. So they calculate the attention in each of these boxes here, and then they combine them together, basically with the concatenation. And another interesting thing, the one we saw before, is that they don't use just one R or one W. They use a sequence of R and Ws. And we will see here that this sequence of R and W are geometric sequences with an alpha constant here. So in this case, the alpha constant is 2. Basically, what they do is they start with a small window. So W1, for example, equal to 4. Then each time you multiply the previous window by 2, and also the dilation rate by 2. So from 4 we go to 8. From 8 we go to 16 until we reach the sequence length. The same happens with the dilation rate. At the beginning we don't skip any word. Then we start skipping 1. Then we multiply it by 2 and we skip every 3. And they combine all of this together using these two equations. Basically, they calculate the denominator of the softmax for each of these attentions, so all of this, and this, and then they use it as a weight for a weighted average. We can see it here. And how to transform this into a multi-head attention? Well, basically, before for each of this combination of segment length and the dilation rate, suppose we have 4 heads. The segment length is 8 and the dilation rate is 2. As you know, with the dilation rate of 2, we need to skip every second token. So we can calculate it like this. For the head number 1, we start from 0 and we skip every other token. So we calculate from 0 and then we skip the 1, and then we skip we arrive at the 2, and then 3 we skip, and the 4, etc. Otherwise we can skip the 0 and we start from the 1. So we we skip 1 and then we do the other, and we keep the same dilated rate. For the head number 3 and the head number 4, we do the same. In this case, the head number 1 and the head number 3 are the same, because actually the stride is smaller than the number of heads. If we had a stride that was bigger than the number of heads or equal to the number of heads, we would see 4 different patterns here. But the basic idea of the multi-head is this one. And let's look at the computational complexity of this model and how it is calculated. Well, the computational complexity of this attention mechanism is basically given by the dot product that we do to calculate the attention. So the softmax of the query multiplied by the key. And with the vanilla transformer, we had n to the power of 2 multiplied by d. But here we have w divided by r to the power of 2 multiplied by d. So w is our segment size. So let's go here. R is the dilation rate. And what we can see here is that the number of dot products that we are doing is this one. So the size of the window is W divided by R. So W divided by R is 4. So this is the size of the window, right? And W divided by R is also the number of tokens in this window for which we will calculate the dot product. Because you can see that this matrix here, even if the size is 8, the number of actual dot product that we will do is actually not 8 by 8, but 4 by 4. Because we are skipping every other token. And even if the size of this window is 16 by 16, we will not be calculating 16 by 16 dot products. We will be calculating 4 by 4 dot products because we are skipping 3 tokens. And this is the idea behind the calculation of the complexity. The fact that we are not calculating the dot product between all the tokens in a window, but only W divided by R multiplied by 2 is the number of the size of the dot products that we will do. And each dot product involves a vector of dimension d, so we also multiply it by d. And divided by W is the number of boxes. So for example, if we are here, if when W is 4, the number of boxes is also 4 because n divided by W 4. And when the number the W is 8, the number of boxes is 2 because 16 divided by 2. And when the sequence length is 16, so W is equal to 16, the number of boxes that we get is 16 by 16, so only 1. So we can see that the number of floating point operations that we are doing is proportional to n divided by 2, so the number of boxes, and in each box we will do W divided by R to the power of 2 multiplied by D operations because of the dot product. And you may be wondering that the window size is still very big, right? So if you do it in NumPy or in PyTorch, actually the number of operations you will do, for example, for this window of size 16 by 16 is still 16 by 16. But there are better ways to represent what are called sparse matrices. So this actually is a matrix that is sparse. So if you create a matrix multiplication algorithm that knows this and that can take into consideration that this matrix is sparse, then you can do many less operations. First, you can store less information because you know that most of the matrix is 0. And the second thing is that you can perform less operations. So if you can just skip calculating the dot product for all the positions of this matrix that are 0, then you do less operations. And I think the authors of the paper, they created some custom kernel for CUDA to do this. Another thing the author shows, okay, here this is the number of floating point operations for one window size, so for one W. But we don't have one W, we have many Ws, and we also know that these Ws are according to a geometric sequence as written in the paper. Written here, we set W and R to geometric sequences. Geometric sequence means that we take the previous W and to get the next W we multiply it by 1 alpha, and this alpha is fixed. Starting from W0, or here for example W0 is equal to 4 and the dilation rate R0 is equal to 1, and every time they multiply by 2. And let's go back here. Okay, so they need to combine the floating point operations for all of these W and R's, and they do it here. But considering that this W and R are actually the result of a geometric sequence, this becomes depending on alpha and W0, so the initial W that you choose. And if we watch this expression here, we can see that it's the number of floating point operations that you need to do calculate this combined attention here. So the combination of all these W and R's here is proportional to n and d. It grows linearly with n and d, so just like it's written here. Another interesting fact is that even if two words are not connected to each other directly by a dot product, we can calculate the information distance between them. That is, how many jumps you need to make to go from one token to the next. Let me explain this better. For example, let's watch my notebook that I made here. This is a notebook that I made specifically for learning this model, and I wanted to actually test how it works. So we imagine we have a sequence length of 16, And so here in the my representation is from 0 to 15, not from 1 to 16, but the idea is the same. And we know that we will be calculating, for example, the first attention will be calculated for this box, this box, this box, this box, then another one that will be this one, and the last one that is this one. And this is exactly the same as the combined attention that we see here. So the overlapping of this attention is exactly the same, just the colors are different. Now let's look how the words, for example, the token number 0 and the token number 15, so the last token, are related. The idea is that we cannot go from token number 0 to token number 15 directly, because there is no dot product between 0 and 15. But we can find a path to go there. So from 0 to 15, we can go from 0 to 12 and from 12 to 15. Let's see. So from 0 to 12, there is a dot product, right? Then there is a dot product between 12 and itself, because in the attention mechanism, we are always making the dot product between every node, every token and itself. And the token number 12, it's related to the token number 15. So there is a dot product between the token number 12 and 15. So actually, the token number 0, it is related to the token number 15 through the token number 12. And we can find this path for all the tokens. And I can prove it, I show it in this notebook that, for example, all the nodes are reachable from the node number 0. So from the token number 0, we can reach all the tokens by using different tokens as intermediate. And in this paper, let's go to the paper. Here, they show that the maximum number of jumps that you need to make to go from one token to any other token is less than, grows with the logarithm of the sequence length. That is, if the sequence length is let's say 10 times bigger, you don't need you don't need to make 10 times bigger jumps to go from one token to the next. This also, so why are we talking about jumps? Because it means also how strong is the relationship between two tokens. Because if we calculate the dot product between two tokens, then that means that the model will find that immediately, that dot product. So the model will learn to relate immediately that two tokens. But if we have intermediate tokens, the model will take more iterations to find this connection between tokens. So the connection between those two tokens will be more weak. And this is what the authors claimed. They claim that the attention mechanism is spread in such a way that the strength of the attention mechanism becomes weaker exponentially with by increasing the sequence length. And or in other words, we can say that the number of jumps that you need to make grows with the logarithm of n. And we can do the same, for example, with other length of tokens. For example, here I use the token sequence of sequence length of 16, but we can use 32, for example, and visualize it. And let's see if it's visualizable. Yeah. So basically, our LongNet will do this. He will start with small boxes of size 4. Then he will also calculate the attention for the box size 8. Then also for the box size 16, and also for the box size 32. Here we can see the overlap attention maxes, so all the different sizes, but also all the single groups. So for example, all the tokens that are directly connected to each other with different color. So the token number 0 is directly connected to the token number 3. And also the token number 4 is directly connected to the token number 5, because they are part of the same box when they are calculated. But the other tokens, they have to be inferred. For example, with the sequence length of 32, we can see that still the token number 0 is reachable from every other token, but by different number of steps. For example, to go from token number 0 to token number 17, we need to pass from 16. Let's see. From 0 to 17, we cannot go directly because there is no dot product here. But we can go to 16. There is a dot product here. And 16 is related to itself also. And 16 is also related to 17. So we actually can go from 0 to 17 by passing from 16. And this can be done for all the nodes. And I also made a graph here to visualize this. So from 0 we cannot go directly to 17, but we can go to 16, and from 16 we can go to 17. And this is the idea of the LongNet. Let's go back. Okay, we don't calculate all the dot products to each other with each other, so all the tokens with all the other tokens, but we spread this attention mechanism in such a way that words that are very close to each other are directly connected, and words that are far from each other are connected through other tokens. And let's watch also. In the paper, they also show how the model can be trained in a distributed way. Well, we already saw it, because all of these boxes are actually independent from each other. So to calculate, for example, the attention in this box here, you need only the embedding of the token number 0, 1, 2, and 3, and that's it. To calculate the attention of mechanism of this box here, you need to have the embedding of the token number 0, 2, and 4, and 6, but not of the other. And to calculate this one, the same, etc. And another interesting thing is that the number of dot products in each box is always constant. So if we have, we can choose the model in such a way that each computer can hold at most that number of dot products. And so this mechanism is quite parallelizable. And it's really important, it's really important because it allows us to scale greatly with the, because parallelization is very important for us, because we can compute the model on the cloud or on different GPUs, and we can take advantage of this parallelization. Another interesting thing is that the runtime, we can see here that with the sequence length increasing, we grow linearly with the runtime, but not like exponentially with the vanilla transformer you can see here. And then in the rest of the paper, they show how the model performs to other previous models. Now, my point is also not to show actually the results, which you can look by yourself. My goal was to actually show the attention mechanism of this new LongNet. And I hope it was clear. I hope also you will use my Python notebook to experiment by yourself. I show you how basically it works. Here you define the sequence length that you want to visualize, and the notebook will only visualize short sequence length. I think I set this to 32. So if it's bigger than 32, it will not be visualized, because it's not easy to visualize it also. And basically, to calculate the distance between one token and the other token, I just basically do a BFS, breadth first search. It's a very ugly one, unoptimized one, doesn't matter, because I built this notebook in half hour just for showing how the model works. So you are invited to make it better if you want. Last thing that I didn't show, and that is very interesting, is that we can see that the maximum node distance from the node from 0 to any other node is 3, and it's changing with the logarithm of n, as you can see. So if we are, for example, if our n is equal to, let's say, 16, let's do it again. If the sequence length is 16, we can see here that this is the path to go from the node number 0 to any other node, and the maximum distance to go from node number 0 to any other node is 2, and it's just like the logarithm of n, which is 16. You can also change which node you want to go from. So if you want to calculate other paths, for example, here we say that I want to go from node number 5 to every other node, and here we prove that the node, all the nodes are reachable from the node number 5, and here we display the paths. Okay, and this is the maximum distance from node number 5 to any other node, and this is the graph. I hope you liked my video, guys, and I hope it was more or less clear how this mechanism works. I didn't explain all the equations. Here I have a lot of comments written on the sides, because I like to take notes when I read the paper, mostly because I want to understand also the maths behind it. So if you're interested in some parts, just write in the comments and I will try to explain it better. But I think most people just want to understand the mechanism, and they are waiting for the official code to be released to actually watch how it works. And I hope I didn't make any mistakes, because basically there is no information online about the LongNet, so everything I told you is all because of my research. And I hope you enjoyed the video, so please come back to my channel for more videos about deep learning and machine learning, and have a great day.